Start the recording. Okay, so least squares problems. Remember what we're always trying to do. We're always trying to solve a system of equations given by a times the vector x equals some vector b. But the problem is in reality, sometimes you cannot solve that system of equations. Okay, you cannot solve it. For instance, some types of linear models given some data. So what do we do? What do we do in that case? Well, if we can't solve that system of equations, ax equals b, what we can do, hold on here, is try to find the approximate solution, vector x hat, okay, such that the distance, so to speak, between the vector b and a times x hat, that distance is smaller than the distance between the vector b and any other vector x. Okay, and we call that vector x hat our least squares solution. Now, if we go to the picture here in figure 1, they note that the vector, geometrically, if you can't solve a system of equations a times x equals b, then that means the vector b is outside the column space of the matrix A. And that's what they're showing in figure 1. And what they've done in figure 1 is they've drawn in the column space of A 3 different linear combinations of the column vectors of A times a vector x1, a times a vector x2, and a times a vector x hat. Okay, so remember, each of those is a vector in the column space of A, but the vector, how do we get the vectors? Those vectors are simply a linear combination of the column vectors of the matrix A. And it turns out that the vector a times x hat is closest to the vector b. So the a times the vector x hat is the vector in the column space of A that's the closest vector to the vector b, which is vector b is outside the column space of A. And so geometrically, that's what the least squares solution x hat is going to be. And of course, and that's just the projection, right? A times x hat is simply the projection of the vector b onto the column space of the matrix A. Okay. Now, how do we find that projection vector? How do we find a times x of hat, which you notice they're calling b of hat? Well, of course, if the column vectors of the matrix A are orthogonal, then you could find that projection vector using the techniques you learned in section 6.3. Okay, but more than often than not, you don't have a matrix A with orthogonal column vectors. And so what they did was they noticed that, well, okay, for every column vector, okay, every column vector A sub j of the matrix A is orthogonal to the difference between the vector b and a times x hat. That's that vertical vector. So the orthogonality means the dot product equals 0, and of course that's true for every column vector in the matrix A. And if we put it all together, we'll end up then having this matrix equation: A transpose times b minus ax hat equals the 0 vector. We can solve that. We can solve that then to get A transpose A times x hat equals A transpose times b. And those are called our normal equations. And the normal equations are how we are going to solve it's how we're going to find the x hat. So we looked at some. Well, are there any questions on that before we move on? This is just a quick review of what you learned last Wednesday. All right, all right. Well, so naturally then, you know, they have some examples here. Okay, so in the one example, example one, and you actually did this in your notes, they have a matrix A and a vector B. A times x equals B cannot be solved. There's no solution vector x. And so they find the least squares solution. So the fact that x transpose times AX equals A transpose times B means then that x hat is just equal to the inverse of A transpose A. Let me go down. X hat is just the inverse of A transpose A transpose times B. And A transpose A is invertible. It has an inverse because the column vectors of A are linearly independent. Okay, now if the column vectors of A are not linearly independent, then you learn, as they show here in example 2, you have a situation where the matrix A, because the first vector equals the sum, the first column vector of A is the sum of the second, third, and fourth column vectors of the matrix A. Those columns are not linearly independent. So A transpose A would not be an invertible matrix. So in order to solve that system, well, in order to solve for the normal equations, I should say, you have to do it this way, where you have to solve for A transpose A and A transpose B, and then you'll end up with a you know, an augmented matrix, okay, for your normal equations. And it turns out in this case that the least squares solutions, that there's an infinite number of them, because the x hat vector has a free variable in it. And so this is, of course, not a very useful situation because you know, we really are looking like when we look for a line of best fit between data points, we want just one line of best fit. That's really a least squares problem. So this is, of course, not a very interesting situation when the column vectors of the matrix A are not linearly independent, and it doesn't happen that often. But nevertheless, we need to be aware of it. So that's really in a nutshell, a little review of what we learned. And they mentioned here in example 4 about alternate calculations of least squares solutions. It's worth just pointing out, in this example 4, you have a matrix A whose column vectors are orthogonal. Okay, you see that in the matrix A in example 4. The column vectors there are orthogonal. The 1, 1, 1, sorry, 1, 1, 1, 1 vector is orthogonal to the vector -6, -2, 1, and 7. So in that case, the projection vector B hat, you can find that using what you learned in section 6.3, the formula from the the formula from the orthogonal decomposition theorem. Okay, you can just use that formula, and they do, because, you know, make your life easy if you can make it easy. And it turns out then that the projection vector is going to be -1, 1, 5/2, and 11/2. Okay. Now they mentioned that since B hat's known, we can solve it to solve for the least squares solution x hat. But that's trivial because we know that we would just hold on. Let me just see here. Yeah, it's clear from equation 5 the projection vector b hat is equal to 2 times the vector a1. Okay, 8 over 4 is 2, plus 45/90ths is a half. So the least squares solution is 2.5. All right, so I want to make sure you're clear on that, because there's really a lot of good geometry here. Hold on, let me make sure. So you see, here's the b hat. We end up with 8/4 a1 plus 4/95 a2. So x hat, we got 2.5 for the elements of the least squares solution. Maybe give me a thumbs up if you're. Hold on here. There's one thing else. I want to take this off. I want to have highlighted only what should be, what's relevant here. Are we okay with the x hat y equals 2.5? Okay, Eleanor's good with that. Thank you, Eleanor. And Abby is wonderful. Okay, great. And oh yeah, here they have the 8/4 and the 45/90ths. Now, they make a comment here. In some cases, normal equations for a least squares solution can be ill-conditioned. Okay, let me just highlight this. Yeah, in some cases, normal equations for least squares problem can be ill-conditioned. That is, small errors in calculations of the entry of A transpose A can cause relatively large errors in the solution. And again, that's because if you're taking an inverse, well, I mean, anytime you take an inverse, if you're able to take an inverse, it can introduce errors, round-off errors, relatively speaking. They mention if the columns of A are linearly independent, the least squares solution can often be computed more reliably through a QR factorization of the matrix A. And you learned that back in section 6.4 when you learned about the Gram-Schmidt process. With the Gram-Schmidt process, you learned about QR factorization. Okay, that's where a matrix A, if it has linearly independent columns, A can be factored as Q times R, where Q is a matrix that has an orthonormal basis for the column space of A, and R is an upper triangular invertible matrix. Okay, so how many remember QR factorization from section 6.4? That's something that okay, Eleanor recalls it. Okay, thank you, and Catherine does. Excellent, thank you, Catherine. Thank you, Eleanor. And so, here they have a theorem 15, that says if you have an n by n matrix A with linearly independent columns, let A equals Q times R be the QR factorization of A, as in theorem 12. That was the theorem from section 6.4. Then the equation AX equals B has a least squares solution, okay, given by x hat equals R inverse times Q transpose times the vector B. Now, the proof of this is actually pretty interesting. What they do is the following. They say, all right, well, let x hat define it to be R inverse times Q transpose times B. Take A times x hat. A times x hat, well, A is equal to Q times R. So A times x hat is Q times R times x hat. Okay, but now hold on here, one moment. Let me see. Okay, now they're replacing x hat by R inverse times Q transpose times B. And they end up getting then, since R times R inverse is the identity, they get A times x hat equals Q times Q transpose times B. Okay, that's what they get. But they note that the columns of Q form an orthonormal basis for the column space of A. Okay, because Q is an orthogonal matrix, right? Q is, now hold on here. Right, an orthogonal matrix is a matrix whose columns are orthonormal. So Q times Q transpose is simply the orthogonal projection of B hat on the Q transpose. Let me highlight it here. Hold on here. Let me unhighlight a few things here just to. So Q transpose times Q times B is the orthogonal projection, B hat of the vector B onto the column space of A. That comes from theorem 10. How many recall that in section 6? That was back in section 6.3. Okay, very good, Eleanor. Excellent, excellent. So, you know, so now that shows that A times X hat equals B hat. So this is just another way to find a least square solution, you know, so they do an example down here. They do an example. Are there any questions before we move on? All right, very good. Very good. So they have an example here, whoops, where they want you to find the least square solution of the system AX equals B for that matrix A and that vector B. And the matrix A, of course, has linearly independent columns. Okay, it does. And what they do is they get the QR factorization of the matrix A. Now, whoa, they just come up with this, hey, here's the, hey, here's the, here's the QR factorization. Hold on now. Do an example 5. So how did they get this QR factorization? They're saying the matrix Q is it's a matrix with orthonormal columns, but how did they construct that matrix Q from the matrix A? What procedure do they use from section 6.4? The matrix A has 3 column vectors that live in 4-dimensional space. The column vectors of the matrix A are clearly, they're linearly independent, but they're not orthogonal. Okay, so how are you going to, so the column vectors of the matrix A form a basis for the subspace spanned by those column vectors, but we want an orthogonal basis for that subspace. So how would we construct an orthogonal basis? What procedure would we use? That's right, Benjamin, the Graham-Schmidt process. The Graham-Schmidt process. So they, of course, the Graham-Schmidt process, you'd pick one of the 3 vectors in the matrix A as your starting vector, and then you would do 2 iterations of it to produce your orthogonal basis. And then you have to once you have an orthogonal basis, you have to normalize your orthogonal vectors to get that matrix Q. Okay, and then the matrix R, remember, the matrix R, right, based on section 6.4, the matrix R is equal to, hold on here, the matrix R equals Q transpose times A. And that's hold on here. Yeah, and so they're not showing all that work, right? There's a lot of work involved there, but but you know how to do it because you've done it before. So okay. Then what they do is they find Q transpose times the vector B. They find that, and then so that's not hard. And then they note that the least squares solution has to satisfy the equation R times X equals Q transpose times B. So now how are they getting that? Well, they have it in this numerical note above. They have R times X equals Q transpose times B. And one moment here, let me just give me one moment here. Let me see. One moment, class. I'm trying to see if I can I want to derive it for you, but I guess yeah. So how are they getting that? How are they getting that? Let me show you. So okay, so you know that x hat is equal to R inverse times Q transpose times a vector B. So that means if we multiply on the left of this equation by R, by that matrix R, then indeed R times x hat will equal, this is a transpose here, right? R times x hat will equal Q transpose times the vector B. Okay, and so you can solve this system of equations generated by that matrix equation and that's what they're doing. That's what they're actually doing in example 5. Are there any questions on that? Before I'm going to go back to example 5, but are there any questions? Okay, so I for some reason the book, what they'll do is they'll write this equation as R times X without the hat equals Q transpose times B. They'll write it that way. I don't know why they don't put the hat in, but they don't. So if we go back to the book, then okay. Here's that equation, R times X equals Q transpose times B. And so in the example 5 below, they get hold on here. Let me kind of get rid of a little bit of yellow here. They get Q transpose times B. Okay, there. And Q transpose times B is equal to 6, negative 6, and 4. That's what they have here on the right side. And then on the left side, they have the the matrix R times the vector X. And so it's a system of equations, and it can be solved. It can be solved. And they solve it, okay, and they get this as the least squares solution, X hat. Are there any questions on that? Who's feeling good? Maybe a few thumbs up if you're feeling good. Okay, Eleanor's feeling good. Excellent. Name is feeling good. Excellent. And Benjamin, wonderful, wonderful. Okay, well then I will, and I'll just mention now, like for instance, in your homework and final exam and all that, these least square solutions, there's typically instructions in the problem on like what you have several ways to find a least square solution now. And sometimes it'll say use the normal equations, or and of course this example 5 is not using the normal equations. This is using QR factorization to get the least square solution. So what I'm trying to say is on the final exam, I'm going to test you on maybe multiple ways to get least square solutions, and it should be clear in the instructions which way it is to be done. And if it's not clear, I'll add instructions when I do the announcement for the final exam. But all right, well then let me stop there.